Hello, everyone. So we're going to continue the discussion about the linear speed and angular speed. So here, I'm just going to proceed of what the formula will be for the linear speed, since I already discussed the background, or rather the introduction to the linear speed and angular speed, and the introduction to linear speed. So if you want to have some recalling information, I suggest you should watch that video, which is Trigonometry, Angles and Angle Measures, Linear Speed and Angular Speed, Part 1. All right? So now let's proceed. So here, for the linear speed, the formula is derived actually from the original formula that we used in physics, which is this one. Wait, hold on. This one. Recall that the formula of the speed, average, this is average, all right, average, okay, is V is equal to D all over T, where distance traveled is D and T is the time, all right? So here, let me give you an example. Let's just say from the initial position up to the final position, you traveled, let's just say 10 kilometers, and the total duration would be 2 minutes. So what would be the speed? So you can use this formula, distance all over t, all right? So we have 10 kilometers all over 2 minutes. Wait, 2 minutes. There you go. So you will have 5 kilometers per minute. That means in 1 minute, you can reach 5 kilometers. And that shows how fast you are. So the thing here is that when it comes to getting a distance, it's actually easy. Like, even if it's only in a linear way or not, like for example, from here, then here, then here, then here, then there, even if it looked like this one, you can get the total speed, like from here up to here, or here up to here up to here up to here, or any point, you can still get the speed, all right? So all you need to do is just add the distance traveled. All right, like for example, starting from here up to here. So let's just say this is 5 meters, 2 meters, 3 meters, 4 meters. Then this is just let's just say 3 meters. So if you want to get the speed from start to finish, all you need to do is add all the distance, then divided by the time duration that you reach from this point up to this point. And that's it. That's how you get the speed. However, uh, on this case, it's similar, but the path is not linear just like this. Rather, it is non-linear, like this one. The ball moves in a circular path. So let's just say if the ball stops here and it reaches, let's just say 1 minute for the yellow ball to reach here. So the question here is that how fast does this ball go from here to here? So of course you need the distance, right? So the distance would be the arc length of the circle. Therefore, since the arc length can be represented as a distance traveled by the ball, we have the formula D is equal to S all over T, where your S is the arc length. All right? So if you forgot what arc length is, I suggest you should go back to my video that I uploaded, which is Trigonometry, Angles and Angle Measures, Length of a Circular Arc. All right? It's just one part video actually, because it's just easy to discuss it. Right? So now let's have some examples. This is actually a ball, not an object. I mean, ball is an object, but to be specific, it is a ball. So, a ball moves in a circular path. What will be its linear speed when the total duration of the movement is 2 minutes and the distance traveled by the ball is 2 meters? So if you're going to visualize it, let's just assume that this is a circular path and you start, let's just say, here. No, here. You start from here. Then after 2 minutes, you've reached a total of 20 meters, right? From here up to here, you've reached 20 meters when you've reached 2 minutes. So what would be the speed? You know, speed from the start up to finish, which is 20 meters in total. So you're going to use this formula, distance all over t, or d all over t. So your d is 20 meters and your t is 2 minutes. So the answer is 10 meters per minute. All right, that's the answer. So what does it imply? It implies that the ball can move 10 meters in 1 minute. So that's how fast the ball is. So you can leave this as your final answer, by the way. Or if you want to convert the minute into seconds, then there would be no problem for me at all. All right. So let's try converting the minute into seconds. Recall that in 1 minute is equivalent to 60 seconds. So if you're going to convert 2 minutes into seconds, you will multiply it by 60 seconds all over 1 minute so that we can cancel the minutes. So cancel, cancel. So we have 20 times 60 seconds all over 1. The result is 120 seconds. Now, divide the distance, which is 20 meters, by 120 seconds. What would be the answer? So approximately this is 0.17 meters per second. So that means in 1 second, a ball can travel 0.17 meters. All right. So this is also correct. So it's up to you. All right. It depends on the given. So it doesn't state if it's in seconds, in minute, or in hours. So it's better to keep it that way. All right. So now we can proceed to the second example. Suppose you have a rope. You rotated it vertically. If the tip of the rope, the one that is moving, not the one you're touching, traveled 15 feet at 5 seconds, then what would be the linear speed of that tip? So to visualize it, imagine that this is you and you're going to rotate the rope. So let's just say the rope is just hanging like this and you're going to rotate it vertically. So that would be like this. So this blue circle represents a circular path traveled by this tip, right? This tip, the end tip of the rope. So let's just say it started from here. Then at 5 seconds, let's just say it's here. All right. So from the start up to the finish, it's 15 feet. Right? It's 15 feet from start to finish. So what we're going to do now is we're going to find the speed of how fast does this tip reach up to 15 feet. And its duration is 5 feet. 5 feet. No, no, no. 5 seconds. All right. Damn, that caught me off guard. All right. So now let's substitute. V is equal to, oh, not D, not D. It's S because we're talking about arc length. All right. So S all over T. So we have 15 feet all over 5 seconds. So the answer is 3 feet per second. So that's how fast is the tip of that rope. That means in 1 second, the tip of that rope can reach 3 feet or will reach 3 feet. So that's it. That's the answer. 3 feet per second. Let me box that answer. Yay. At least now you get the idea of how you will get the linear speed of an object. All right. So now we're going to proceed to the angular speed. Suppose we're going to have actually a break because before, right, we discussed the introduction to linear speed and angular speed. Then we stop until the introduction to linear speed, right? So it's up to you if you're going to pause yourself, take a break, then continue watching this video for at least, let's just say, no, no, no. I mean, you can take a break, let's just say, for at least 5 minutes, but at most 10 minutes. All right. Then come back here, or you can just continue watching this one. All right. Since the break cycle here is broken because we finish early, like from the introduction of this subtopic up to the introduction to linear speed. All right. So you can pause this one if you like to, like 5 minutes or 10 minutes, then come back here, or let's continue. All right. By the way, this is the reference. I forgot also to put references in the description in a YouTube video. So I would suggest I should put it on the description next time. So, anyways, let's continue. Angular speed. So the same example. Suppose a yellow ball moves in a circular path. All right. Then the ball stops there. This is your final position. Now the question here is, oh, what's this? Wait, what's this? Ah, by the way, forgive me. There are like my drawings last time. Forgive me. So yeah, anyways, the question here is this one. If if 135 degrees is the distance between the start and the final position of the yellow ball, then how fast does this angle form? So earlier we know about linear speed, right? So if this is your initial, then this is your final. So how fast does this ball moves from the initial up to the final, right? So all you need is the arc length, then the time. Now, for this case, okay, it's similar, but we're not talking about the arc length. We're talking about the angle or the angular distance between the two balls. All right. The ball that is in the start and the ball that is in the final position. So we're talking about angular distance. So how fast does this angle form from this point up to this point? How fast? So we're going to use this formula. All right. So the formula is just similar as the formula of the speed, which is v is equal to distance all over time. All right. As usual, you need the distance, but we're talking about angular distance, right? Angular. Angle, right? Angle. So therefore, we're not going to use d, but rather theta. All right. But remember, there's one thing that you need to be careful of when it comes to substituting any value that is an angle. Make sure that this is in radians. Okay? This is in radians. All right? Again, this is always in radians. Just like in the arc length, right? Arc length is equal to r times theta. If you recall that I told you that the angle should be in what? Should be in radians, right? So the same explanation here as well. You need to use radians here, not degrees, okay? Not degrees, but rather radians. Since radians is unitless, that would be much more valid to use radians. So therefore, the angle should be in radians, not in degrees. Angles are let's just say allowed to use here, but uh, based on my research and my experience when I was a high school student, the angle should be always in radians. All right, not in degrees, but rather in radians. Okay, but there's another thing that we're going to change. We use v to represent linear speed, right? Earlier, we have v is equal to s all over t. In fact, v is actually the overall representation of the speed, just like this one. So here, to avoid confusion, we would rather use w to represent angular speed. So therefore, the formula of the angular speed is W is equal to theta all over T. All right? So why is it W again? To avoid confusion between the linear speed and the angular speed. All right? They have the same representations, but the only difference is that not only that the linear speed use the arc length, and on the other hand, angular speed use the angle, but it's also because that they use the same letters to represent speed. So therefore, to avoid once again confusion, we would rather use different letters to represent any type of speed or another type of speed. So that would be W as for the angular speed and B as for the linear speed. So now let's proceed. Let's have some examples here. Wow, that's too direct. But anyways, so here, an item travels in a circular motion when the angle between the object's starting location and the final position is 2 pi all over 3 radians, and the time it takes to form this angle is 6 seconds, what will be its angular speed? Let me repeat that. An item travels in a circular motion when the angle between the object's starting location and final position is 2 pi all over 3 radians, and the time it takes to form this angle is 6 seconds, what will be its angular speed? So remember that the formula is W is equal to theta all over T. So since the angle is in radians, so we can now easily substitute the given. So the theta here is 2 pi all over 3 radians. And the total duration here is 6 seconds, right? So what would be now the answer? Actually, this is already the answer, but we need to simplify this. If you're going to simplify this fraction, this would be 2 pi all over 6 times 3 is, I do believe, 18, right? 18 seconds radian. All right? But 2 and 18 are both divisible by 2. So 2 divided by 2 is 1 and 18 divided by 2 is 9. Hence, you have pi all over 9, radian per second. Wait, I forgot to put per second on after the radian. Yeah. All right? So that's it. All right? So here, we're going to approximate this one. All right? Approximate this one. So this one, if you're going to get the decimal value for, let's just say, until 2 decimal places, this would be 0.35 radians per second. 0.35 radians per second. So what does it mean? It means that approximately you can reach 0.35 radians in 1 second. So that is the answer. So let's have one more example. Consider a line segment that rotates until it reaches its end place in a clockwise rotation. The angle created from beginning to end is 100 degrees. In terms of angular distance, how quickly does the line segment rotate until it reaches its final position when it only takes 36 seconds? So that would be easy as well, all right? So according to the given, we have an angle created which is 100 degrees. So we have the theta as 100 degrees. However, this is not in radian, so we're going to convert it into radian. Recall that if you're going to convert a degree to radian, what you will do, multiply the angle that is in degrees by what? By pi all over 180 degrees radian. All right? So we will multiply this one by pi all over 180 degrees radians. These two, 100 degrees and 180 degrees, are both divisible by 20 degrees. So 100 degrees divided by 20 degrees is 5 because 5 degrees times 20 degrees, that will be 100 degrees. Next, 180 degrees divided by 20 degrees is just 9. Am I right? Sorry, I am doubting myself too much. Oh, wait, no. 180 divided by 20. All right, so it is 9. Now we can now simplify. Oh, it's simplified. So we can now have this simple expression or simplified expression, I mean. So 5 times pi all over 9 radians. So the answer is 5 pi all over 9 radians. That's it. Now we can now substitute it in our formula. So W is equal to theta all over T. So your theta here is 5 pi all over 9 radian all over the T, which is 36 seconds. So this one, if you're going to get the exact answer, 9 times 36, you will have 324 radian per second. So let's get the approximate answer for this one. All right. So I'm going to do this quick. 5 pi all over 324, you will have 0.048, 0.048 radians per second. So that means in 1 second, you can reach 0.048 radians. And that is all. So let's have a break. All right. So see you soon in the next part of this video.